In this podcast, we'll discuss the phenomena of absorption and emission of electromagnetic radiation, which are the basis for a number of optical analytical techniques, including UV visible spectroscopy and fluorescence spectroscopy. At the end of this podcast, you should be able to 1. Explain the phenomena of absorption and emission, and 2. Be able to understand how electronic energy diagrams can be used to visualize and explain these processes, and 2. Draw and use a Jablonski diagram in order to explain the difference between fluorescence and phosphorescence and show how internal conversion and intersystem crossing participate in the emissive processes. Let's begin by talking a bit about the phenomena of absorption and emission in general terms. In general, when electromagnetic radiation is incident on an atom or molecule, if the energy of the photon is just right, the energy of the photon will be transferred from the photon to the atom or molecule, and it will induce a transition from one energy state to another, a ground energy state or a stable energy state, to a higher energy state, one that is less stable. It should make sense that once this happens, the so-called excited state, which is energetically unstable, will want to find some way to return to the ground state. Sometimes, under the right circumstances, this will happen through the release of energy in the form of a photon of light, and we refer to this second process as the process of emission. It's important to keep in mind that depending on the energy of the electromagnetic radiation, the transition can produce different changes in the atom or molecule. In the ultraviolet or visible spectral range, the energy of light produces changes in the electronic configuration of the atom or molecule. However, if the energy of the electromagnetic radiation is in the infrared spectral range, absorption of infrared radiation will result in vibrations. How, on the other hand, if radio wave electromagnetic radiation is used, nuclear transitions will occur for selected nuclei. All of these changes can be used to learn about the structure of matter and to quantitate how much of a material is present. In this podcast, we're going to focus on the interaction of UV and visible light with matter. In the ultraviolet and visible spectral range, when light is incident on a chemical compound, if the energy of the light closely matches the energy between the two electronic energy states, absorption may occur. The energy of the photon is transferred to the atom or molecule, and this results in a promotion of an electron from the lower of two electronic energy levels, from the lower one to the higher one. Once this happens, it should make sense that the molecule or atom will now be energetically unstable because it possesses an energetically unstable electronic configuration. In certain circumstances, which we'll discuss later, the atom or molecule may return to the ground state and in the process give off the excess energy in the form of a photon. This is what we refer to as emission. We often use electronic energy diagrams in order to understand the process of absorption and emission. In these diagrams, you'll typically see a series of vertical lines. Each line corresponds to a different electronic orbital. These orbitals are usually labeled with letters and numeric superscripts or subscripts that indicate the symmetry properties of the electronic, atomic, or molecular orbital. There are two orbitals that are generally involved in absorption, and we often label these as the HOMO and LUMO. HOMO is shorthand for highest occupied molecular orbital, and LUMO is shorthand for lowest unoccupied molecular orbital. The highest occupied molecular orbital is the molecular orbital that is highest in energy for that particular atom or molecule, and it is at least filled with one electron. The LUMO is the orbital above the HOMO that will become populated through the absorption of a photon with just the right energy. That is, the energy that's needed to promote an electron from the HOMO to the LUMO. And here's a generic energy level diagram for the absorption of UV visible light. The incident photon has energy E equals h nu, which corresponds exactly to the energy gap between the HOMO and the LUMO. When a photon with just the right energy is incident on the molecule, an electron, here depicted in green, is promoted from the HOMO to the LUMO. Since there is now a vacancy in the HOMO, the molecule that's produced is energetically unstable, and we refer to this species as the excited state of the compound. In some cases, the excited state molecule will return to the ground state by emitting a photon of light with energy E equals h nu. Now let's delve a little bit deeper into the emission process. If you recall, each orbital can hold a total of 2 electrons, each of which has a different angular momentum. We often differentiate the spin angular momentum in the energy level diagrams based on the orientation of the arrow that we use to depict the electron as either spin up or spin down. This corresponds to a spin angular momentum of plus 1/2 as versus minus 1/2. We often use the terms singlet and triplet to differentiate between states with different total spin angular momentum. If the electrons are spin paired, one electron spin up, one spin down, the total spin or spin angular momentum is 0, and we call the state a singlet state. If the spins are not paired and both are up, plus 1/2 and plus 1/2, or both down, minus 1/2, minus 1/2, then the total spin angular momentum is 1 or minus 1, respectively, and we refer to the state as a triplet. Now let's talk for a bit about how we can use this information in order to explain the difference between 2 different emissive processes known as fluorescence and phosphorescence. On this slide, I'm rendering the HOMO and the LUMO a little bit differently than I did on my earlier slide. Each electronic energy state is actually a band rather than a single discrete level. It's a manifold with a number of closely associated vibrational and rotational sublevels. The specific number of these states depends on the number of atoms in the molecule and on symmetry. The relative populations of these states is given by a mathematical equation known as the Maxwell-Boltzmann distribution. And the bottom line is, energetically, the lower states in the diagram tend to be more highly populated. If there's a pair of electrons in the ground state HOMO, upon excitation, the spin angular momentum is generally unchanged. So if in the HOMO we have 2 electrons and they are spin paired, and a photon comes in and it photoexcites the compound, it will basically leave one electron, say as depicted in this diagram, spin down in the HOMO, and the other electron, when it's promoted to the LUMO, that electron will have spin up, the same spin that it had originally in the HOMO orbital. This excited state molecule that's produced and is depicted on this slide then is what's referred to as a singlet state. It can return to the ground state, this excited state, through a number of different mechanisms, and we're going to talk about them. The first of these is internal conversion, or IC for short. Internal conversion is a very fast process. The time scale is on the order of picoseconds. Internal conversion is a radiationless process, which means it does not involve the emission of photons. Rather, energy is lost by the excited state through the vibrations, which will ultimately generate heat. The second process whereby an excited state can return to the ground state is through fluorescence. Fluorescence is the emissive process in which a photon is emitted in a spin-allowed process in which there is no change in the spin angular momentum for the excited state as versus the ground state. Energy is lost by the production of a photon. The energy of emission is always less than the energy for absorption, and this means that emission is always red-shifted relative to absorption. Fluorescence lifetime is a term that's often used, and it refers to the average time that it takes the molecule before it emits a photon and turns to its ground state. The lifetime for fluorescence is relatively short, on the order of nano to picoseconds. Now, sometimes an excited state will undergo a change in spin angular momentum through a non-radiative process that we refer to as intersystem crossing, or ISC. And it will produce a triplet state, as is depicted on this slide. ISC is a relatively slow process, and it may take from tens of nanoseconds to milliseconds or longer in order to complete. And this brings us to the last process that we call phosphorescence. Phosphorescence is the formally spin-forbidden emissive process which occurs when there is a difference in the spin angular momentum between the excited state and the ground state. The lifetime for phosphorescence is much longer than that for fluorescence. Now, the energy diagram that we have been using in order to look at the various radiative and non-radiative processes that result from absorption is often referred to as a Jablonski diagram. It's a very useful tool in photochemistry, and I'd encourage you to review it and to feel comfortable talking about and using the terms absorption, intersystem crossing, internal conversion, singlet, triplet, fluorescence, and phosphorescence. And with that, that's going to bring our discussion of absorption and emission to a close. And as we close, I would again like to encourage you to take a moment to reflect. At this point, you should be able to, 1, explain absorption and emission, and understand how these electronic energy diagrams can be used to visualize these processes. Draw and use a basic Jablonski diagram in order to explain the difference between fluorescence and phosphorescence, and to explain the role of internal conversion and intersystem crossing in these emissive processes. And with that, this podcast is over.